All right, in this chapter, we'll look at work, energy, and power. It turns out that to do work, you need energy. Okay, so we'll see how the body uses the energy we get from food to do work and other things. Um, so essentially, the energy we get from food, you either do work or bodily processes. Um, a lot of that energy, a byproduct of a use of a lot of that energy is thermal energy, which we need to maintain our core temperature. And then any excess energy is stored as fat for future use. Power is just the rate of use of energy. Okay, so let's see the various concepts in this chapter. Okay, so we need energy to do work. So for instance, if you wanted to lift this box up, um, the chemical energy stored in your body is used to lift this box up. And generally humans, the efficiency is anywhere from 5 to 20%, and we'll see that. Okay, so you need energy to lift this box up to do work. So every bodily process requires energy. Blood circulation, digestion, even sleeping, there's processes going on in your body and you need energy, and thinking as well. So the from an energy perspective, the body, you can look at the body as an energy converter, which with intake of energy being chemical energy. So when you eat food, you're taking in energy, and that energy is used to do many things. So you conduct internal processes, do mechanical work, lift objects, go bicycle riding and stuff like that. When you do this, when you do work and a lot of bodily processes, thermal heat is produced uh, as a byproduct, and then you store any excess energy that you don't use. Okay. Now, if energy is conserved, so if you do 100 joules of work on an object, the when you do 100 joules of work on this object gains 100 joules of energy. So when you lift it up, for instance, if you put in 100 joules of work, it gains 100 joules of energy. Okay. Now, energy comes in various forms. So here are various forms of energy: solar energy, or chemical energy in oil, natural gas, and all that. We broadly classify into mechanical, chemical, radiant, nuclear, etc. Okay. Now, energy cannot be created or destroyed. Okay, so the total energy of the universe, for instance, is constant. Energy can be transformed from one form to another. So, we can, well, electricity is not listed here, but solar energy can be converted to electricity. Plants convert solar energy to chemical energy, and so on. Okay, so energy can be transformed from one form to another and transferred from one object to another. So for instance, in this example, this person lifting up the object transferred energy from the person to the object. Okay, so energy cannot be created or destroyed, but it can be transformed from one form to another and transferred from one object to another. All right, so in everything we do, and that happens in nature, energy is only transformed from one form to another and transferred from one object to another. The total energy of the universe remains constant. So in this example, for instance, with the pendulum swinging, here it has gravitational potential energy, here it has kinetic energy, and back to gravitational potential energy. So this pendulum will swing forever as long as there's no air drag. So you see, but maximum potential energy, maximum kinetic energy, all that potential energy got converted to kinetic energy and then back to potential energy. So it'll go back and forth. Here's the expression for potential energy. mgh, m is the mass of the object, g is the acceleration due to gravity, and h is the height above this reference level. And there is a formula for kinetic energy. Now, it turns out that some conversions are more efficient than others. So for instance, all of mechanical energy is potential plus kinetic energy, can be converted to heat. But when you try to convert heat to mechanical energy, for instance, you do this in your car, you burn gasoline, heat is generated, and you try to convert that to the motion of the car. When you try and convert heat to mechanical energies, your car is only about 20% efficient. Okay, so what we are saying is mechanical energy to heat, you can go 100%. But if you try to convert heat to work, only about 20% of 20 to 30% of that is converted to work, and the rest remains as heat. Okay, so heat is said to be the worst form of energy because to convert it into useful energy is hard. Okay, so here are various processes. So here that occur in nature that or in our technology where one form of energy is converted to another. So for instance, plants via photosynthesis convert radiant energy to chemical energy. And in your bodies, you convert chemical energy via oxidation to other forms of energy, and you can convert it to radiant energy as well. Okay, solar cells convert sunlight, radiant energy to electrical energy. Light bulbs do the opposite, convert electrical energy to radiant energy. Okay. Anyway, so this is showing you all the various transformations that occur. An electric motor converts electrical energy to mechanical energy, and so on. Now we can trace back all of our energy essentially to the sun. So inside the sun, fusion reaction is happening where nuclear energy is converted to electromagnetic energy. This electromagnetic energy is converted to chemical energy by plants. We consume plants, and so we consume this chemical energy. And when we do work, that chemical energy is converted to mechanical energy, which eventually gets converted to thermal energy and radiant energy, and it goes back to space. So it's radiated back to space. Okay, so there's sort of an energy cycle. Okay, so you see various processes where one form of energy is converted to another, and so on. Okay, now here's the technical definition of work. So when this person is pushing on this lawnmower and the lawnmower moves in that direction, the work done by this person, the work done is the force times the distance the lawnmower was pushed times cosine of the angle between the two. Okay, so for instance, F cosine theta, what it does is it gives the component of the force along the displacement. So only the component of the force parallel to the displacement does work. Okay. Here's another way to look at it. When theta is less than 90 degrees, cosine theta is positive, so the work done is positive. When theta is 90 degrees, so for instance, here's in this example, the force is applied in that direction and the suitcase moves in this direction. So here the angle is theta is 90 degrees, cosine theta is 0. And so work done in this case is 0. And here's another case that you encounter often. Okay, so when you apply brakes on your car, the car is moving forward while it's stopping, and the brakes apply force in the opposite direction. And so this angle is 180 degrees. Cosine 180 is -1. And so when the force is acting in an opposite direction, or if the angle is greater than 90 degrees, the work done is negative. Okay. Anyway, so there's the formula for the work done. And so work done by a force can be positive, negative, or 0, depending on what the angle is. Okay. So if the angle is acute, the force is positive. When the angle is 90 degrees, work done is 0. And when the angle is obtuse, the work done is negative. Forces are measured in newtons, distances in meters. This cosine theta has no units. Okay, so A Newton meter is the unit for work, and this is called a joule. So the SI unit for work is a joule. Now we'll define power. Okay, power is the rate at which work is done. It's work divided by time. And to do work, remember you need energy. So power is also the rate at which energy is consumed. Okay. So for instance, let's say you're climbing a flight of stairs. The work you did is the mgh, where m is your mass, g is the acceleration due to gravity, and h is the height you climbed. So that's how much work you did. Okay. Now you can climb the stairs fast, or you can climb the stairs slowly, or you can run up the stairs. The difference is when you run up, you're taking less time. So to do the same work, took less time, and this ratio is what is called power. So your power is greater when you run up the stairs. Okay. Again, work is measured in joules, time in seconds, and 1 joule per second is called a watt. So that's the SI unit for power. Okay. Now, a good measure of rate of work being done is the rate at which a horse does work, and that's called a horsepower. And a horsepower is 746 watts. Okay. A human, if you want for a human to work, put in an 8-hour day, the best we can do is a tenth of a horsepower. So we can work at 0.1 horsepower for 8 hours. So in this problem, here's a simple problem. Here's a nurse lifting a baby, and you can see this is the center of mass of the nurse and the baby. And when she lifts up, the center of mass has risen up that height. So the work done by the nurse in lifting herself and the baby is equal to mgh. M is the mass of both the nurse and the baby combined, because both were the center of mass of both were lifted that height. So calculate the work done by a 50 kg nurse lifting 25 kg child and herself 0.5 meters. So the total mass is 75 kg. There's g and there's the height. Okay. So for instance, if you wanted to calculate the work done just to lift the baby, and if the baby was lifted half a meter, you just use the mass of the baby. Okay. So anyway, here's a calculation. That's the work done. Like we said, we get our energy from foods. Okay. And okay. So the energy content of food is measured in kilocalories. A kilocalorie is 1,000 calorie. Okay. This is also called a food calorie with a big C. Okay. So the food calorie, the 80 calories that you see on a yogurt can is really 80 kilocalories. So 1 kilocalorie is a food calorie. Okay. And by the way, 1 kilocalorie is 4,186 joules. Yeah. So here are some energy content of some foods. So apples on the average have 0.58 kilocalorie per gram, avocados 1.67, and so on. Okay. Roasted chicken 1.06 kilocalories per gram, and so on. So this is a list of food calories. Okay. Now, so when you want to use this, the stored chemical energy in food, the way you release the chemical energy is basically via oxidation. Okay, so you combine glucose with eventually ATP molecules with oxygen, and the oxidation process is complex. It's a several step process and can result in both thermal energy and work being performed by the animals. So let's say you want to go running, you're using the energy stored in the food, and you oxidize the food, and that energy can be used to run. And you also produce heat when you're doing that, because the body is not 100% efficient. Okay. All right. So if the animal consumes more food than it needs to do work or keep warm, so here are a couple of things that we need to do: bodily processes, we need to do work, and we need to keep warm. So, and if you eat more food than what's needed, the remaining food is converted to fat and stored. Okay. So we need energy for our bodily processes to do work. We also need to produce heat, but the heat produced is a site is a it's a consequence of all the other things we do, and we need the heat to maintain our core temperatures. Okay. So, and excess heat, any excess energy is stored as fat. All right, so for instance, so let's say if you eat more food than you need, or you consume more energy than you need. So for instance, if you uh, if you normally require 3,000 kilocalories for food, I mean 3,000 kilocalories of food per day, and you eat 4,000 kilocalories, will show you how much exercise you need to do to burn off that excess calories, those excess calories. Yeah. So it turns out that, so from here you can see that so this table shows you cycling. Okay, so cycling at a normal speed, at a comfortable speed, uses 5.7 kilocalories per minute. Okay, so if you were cycling at a comfortable speed, okay, the 1,000 kilocalories you used excess, okay, so you would burn 5.7 kilocalories for every minute of cycling. You'd have to cycle 3 hours to burn off that 1,000 calories. Okay. So again, we are learning about energy, and here are the various forms of energy. Kinetic energy is the energy in motion. Thermal energy is heat energy. Okay, it's the kinetic energy of atoms and molecules in your body due to the random motion, and that's internal energy. Potential energy, you saw that when you lift an object up, it has gravitational potential energy. Okay, so it can also be, potential energy can come in various forms. It's due to the position, to gravity, or you can stretch a spring and stuff like that. So you can deform an object, and it'll have potential energy, store potential energy in it. Okay. Radiant energy, light is radiant energy, and mass, if you could convert mass to energy, that's a very difficult thing to do, but that's nuclear energy. So for instance, you've all seen this equation equal to E equal to mc square, and that's the energy equivalence of mass. C is the speed of light. Yeah. This is sort of a silly problem. It says if you could convert it, what it shows you is if you could convert 1 gram into energy. 1 gram is that many kgs. There is the speed of light. The energy content of 1 gram is that many joules. Okay, and let's say a person needs 2,000 kilocalories per day. That is that many calories you need per day. And if you convert that to joules, each person needs that many joules. So if you divide this by that, that's 10 million people. Okay, so what this problem is trying to show you is you convert 1 gram of any substance into energy. There's enough energy in there to feed 10 million people. Okay, but of course that's very hard to do. Even the sun over 10 billion years converts only 1% of its mass, or 1 to 2% of its mass to energy. Okay, so converting mass to energy is not an easy thing to do. So in that sense, this is sort of a silly problem. Okay, in this problem, when you slide down a hill, and this problem is done assuming there's no friction, the potential energy, gravitational potential energy, is converted to kinetic energy. And so that's what this is. You have that much potential energy at the top of the hill, and if there's no friction, all of that gets converted to kinetic energy. Okay, and so you can calculate your speed. Okay, the mass cancels. That means no matter what the mass of the person, they'll all be going at the same speed. And so velocity is square root of 2gh. Okay, and this, so if you start off from 100-meter high hill, at the bottom you'd be going at 44 meters per second. Here's a problem that shows you how much power you're using. Okay, or power is the energy over time. So let's say you climb up a flight of stairs, and this is a 2-meter flight of stairs. Let's say your mass is 60 kg. There's the acceleration due to gravity, mgh. You climb, and if you do it in 2 seconds, the power is, if you work this out, it's 588 watts. Okay, so if you climb up a flight of stairs in 2 seconds, that's your rate at which you're spending energy, and this is about 0.8 horsepower. Okay, so that's a pretty brisk pace of climb. Okay, so we are interested in efficiency. Okay, of course you wouldn't want to be as efficient as possible in everything you do. Okay, so efficiency is, we define as useful work that you do, and the energy divided by the energy input times 100. So useful work, efficiency is useful work divided by energy input. And times 100. Okay, so that's efficiency. So energy is always wasted when people, animals, machine, or electrical devices do work. Our energy is not lost. What happens to the wasted energy in a human? So let's say you consume 100 joules of food energy and convert, and 20 joules of that is converted to work. What happens to the other 80 joules? The other 80 joules is converted to heat. Okay, and you use some of this to keep your body warm, and if you have too much heat produced, then you have to get rid of that heat to maintain your body temperature. Okay, so we'll see how you get rid of that heat, the excess heat that your body produces. Okay, so in most circumstances, the thermal energy produced by the body when doing physical work is much more than is needed to keep warm, and must be dissipated. Okay, and one way of getting rid of this excess heat is, one method of getting rid of this thermal energy is evaporation of perspiration. Okay, so what happens is, here's a way to get rid of the heat. So you sweat, and every time, you will learn this in the next chapter, every time 1 gram of sweat evaporates, it takes away 540 calories of heat. Okay, so that is the best way. That's one of the best ways to get rid of heat. Okay, so when your sweat evaporates, every time 1 gram of sweat evaporates, you take away 540 calories of heat. Okay, so you'll also learn in the next chapter. So if the humidity is 100%, then your sweat won't evaporate, and it's hard for you to cool down. Okay. So let's look at efficiency in human bodies. So here's the efficiency for various tasks. Okay, so if you're cycling, you're about 20% efficient. When you're swimming on the surface, 2%. When you swim submerged, you're about 4% efficient. So that's why you guys have seen that swimmers, when they're in when they race, when they dive into, they start off to start the race, they swim underwater as much as possible because they're more efficient, and then they have to, of course, come up and swim on the surface. Okay. Okay, so you again, from an energy perspective, we can thought of the body's an energy converter. We intake energy in food and then convert it into mechanical work, thermal energy, or store fat, and so on. Okay, so again, all bodily processes require energy. Blood circulation, digestion, sleeping, and thinking, they all need energy. And then if you, of course, go for a run and all that needs energy. Okay, so we'll see why our efficiencies are different for different tasks. So shoveling is only 3% efficient. So here's the basic thing. So why does body efficiency vary with activity? It basically depends on how many muscles are used to produce work. The more muscles you use to do a task, to do a useful amount of work, the less efficient the body is. Okay, so here's an important point. The more muscles you use, the less efficient the body is. So a single muscle by itself is about 25% efficient in converting food energy to work. Okay? The rest goes into thermal energy. So you can never be more efficient than 25% because you more often than not use more than one muscle. But if you used just one muscle, you could be 25% efficient. So for instance, well-trained athletes are very efficient. So what a well-trained athlete is uh, they learn to do the same task using this minimal amount of minimal number of muscles. Okay, so and that's why they're efficient. So two individuals performing the same physical activity often have different efficiencies. The person who has the fewest muscles exerting forces in opposition to one another will have the greatest efficiency and will frequently be able to accomplish the most work. Okay. So, all right. So your human efficiency can vary from 2 to 20%. Okay. Now, here's what one of the consequences. Okay. So if you're, let's say, if you're doing a task and you're 20% efficient, for every 100 joules of energy used in the body, only 20 joules went into work, and the other 80 joules you're producing heat. Okay, so when you go for a run, for instance, you're producing a lot of heat. Okay, so the low efficiency of the body means a significant amount of thermal energy is generated, and the portion not needed to maintain body temperature must be dissipated into the environment. And you saw that the best way to get rid of the heat is to sweat and hope the sweat evaporates. And every time 1 gram of sweat evaporates, 540 calories of heat are taken away. Okay, and you saw that when the humidity is high, so for instance, if it was 100% humidity, your sweat wouldn't evaporate, so you would have a hard time cooling. And so here's a technique that's used in the medical industry. One can use. So if it's too hot and your it's too humid and your sweat won't evaporate, what you can do is you can give an alcohol rub, and there's no alcohol in the atmosphere, and so the alcohol will evaporate. The only problem is when 1 gram of alcohol evaporates, it takes away about 240 calories of heat. Okay, or somewhere in there. So it takes away less heat. But again, the advantage is the alcohol will evaporate fast. So that's alcohol rub is a quick way to cool a person as well. All right, so metabolic rate. Okay, so the rate of conversion of food energy to some other form of energy is called the metabolic rate. Okay, so if you're using 500 joules of food energy per second, your metabolic rate is 500 watts. Okay, the total energy conversion rate of a person at rest is called the basal metabolic rate. Okay, so the basal metabolic rate uh, for so this is all these are calculated for assuming, well, for an average 65-year-old male. So the basal metabolic rate is 85 watts, meaning to run this person's body that at rest you need 85 joules of energy per second. Okay, and you see this table lists the various percentage. The liver and spleen almost use a third of that energy. Okay, the brain uses 20%. Okay, so liver and spleen use 27%. The brain uses 20%. Your skeletal muscles use another 18%. The kidney uses 10%, and so on. The human brain has 86 billion neurons. Okay, and it's the most complex energy consuming brain on the planet. So a chimp's brain is not as complex. So for instance, so you need about 6 kilocalories of energy per day to sustain 1 billion neurons. Okay, and to run your entire brain you need 500 kilocalories of energy per day. Okay, so you see about if you're eating 200 kilocalories, about 25% of that energy goes into running your brain. Now, here's an interesting point about food. So, why do we cook food? Cooked food is partially digested and provides the body on the average with 3 times the energy per pound. So, the energy density of cooked food is about 3 times that of raw food. So, for instance, if you just ate raw food all the time, you need to eat about 9 hours like each day to supply enough energy to maintain a healthy human. I guess so. We'd all be like cows, eating all the time. So it was the invention of cooking 1.5 million years ago that has allowed the human brains to evolve to its present degree of complexity. So, for instance, no other primate cooks, and that's why their brains cannot evolve to more complex brains. Again, by the way, the basal metabolic rate of a person is related to thyroid activity. You have an overactive thyroid results in a higher basal metabolic rate. Yeah. It's also related to your mass. Larger people have greater BMRs because you need more thermal energy to maintain body temperature, and also larger organs need more energy. And larger muscles can do more work and so on. Now, your energy consumption, the rate at which you convert your food to energy, is directly proportional to oxygen consumption. Remember, your food, to make it into useful energy form, it has to be oxidized. Okay, so the more oxygen you consume, the faster you're using up your energy. Okay, so approximately 5 kilocalories of energy are produced for each liter of oxygen consumed, independent of the type of food. So you release 4.9 kilocalories of energy per liter of oxygen consumed. Okay, so this is a simple physiological measurement. So because of this, some physiological measurements use oxygen consumption rate as a measure of individual's energy production rate. So that's one simple way of doing it. All right. The human digestive process is quite effective. So let's say you eat food and only about 5% of the caloric content of the food is excreted. Okay. And so the body is able to harness 95% of the calorie content of food. And you already saw that the body stores excess food energy in fatty tissues. During rest, most of the energy consumption of the body ends up as thermal energy. Okay, so all the energy that you're using for bodily functions eventually turns into heat. Okay, only a small amount of actual work is done. Okay, so if you're resting, you're not lifting anything, and so on. So all the energy used is for bodily processes, and it ends up as heat. Okay. So work done by the heart on the blood is eventually converted to thermal energy by friction in the circulatory system. And when you're resting, most skeletal muscle activity is in the form of some small motion during rest. So you're not hardly doing any work there. So this problem says, okay, uh, so if you have no activity, how much fat would you gain uh, for a given diet? Uh, so if you consume 2,500 kilocalories of food, and so your basal metabolic rate is where in this unit is you're consuming at rest, you're consuming 1.22 kilocalories every minute. Okay, so from there, from this number you can calculate that you need 1757 kilocalories per day. And if you consume 2500 kilocalories per day, this is the excess you're consuming, and this turns into so the excess energy turns into fat. You turn Okay, so this is a very simplified problem. Yeah. This you convert to fat, and so uh, you're storing 80 grams of fat every day. Okay, so if you let's say eat 1,000 kilocalories extra every day, you're converting about 100. You're producing about 100 grams of fat. That's what that says. And if you keep doing this for a year, you'd gain 64 pounds. That's what this problem is saying. Okay, so this is an average person, about 65 kg. A person sitting at rest consumes 20 liters of oxygen per hour. And remember, for each liter of oxygen consumed, you produce 4.9 kilocalories of energy is produced for each liter of oxygen. So from here, you can get your basal metabolic rate. Okay. This goes into the details of how you get the 20 liters. Okay. So average respiratory rate of a person is 12 breaths of half a liter. Each breath you're taking in half a liter per minute. Okay, so or so in an hour per minute you're taking 12 breaths. In an hour you're taking 720 breaths. Okay, 60 times that, and that amounts to 360 liters of air. Air is 20% oxygen, so 20% of that is in an hour you're breathing in 72 liters of oxygen. But this is the oxygen that gets to the lungs. Only 28% of that is used. Okay, only. So essentially in an hour you're getting 20 liters of oxygen, and that's what that is. And with every liter of this oxygen, you can produce 4.9 kilocalories of energy. Okay. What happens to the other 72% of the oxygen that you breathe out? The 72% of the oxygen that's exhaled can be used for mouth-to-mouth resuscitation and blowing on charcoals and so on. All right, this problem shows you okay, so here's a cyclist traveling at 21 kilometers per hour. That's quite a brisk pace, consumes 2 liters of oxygen per minute. So they're producing about 10 kilocalories of energy per minute. A person's sleeping is using 0.2 liters of oxygen per minute, roughly 1/8. So that divided by that, So when you're bicycling, you're producing energy at the rate of 8 times that when you're sleeping. Again, that's what this problem is showing you. All right, so we have an aerobic phase and an anaerobic phases in our bodies. Okay, okay. So what are these? So in the anaerobic phase, humans and other animals can work for short periods of time at much higher rates than can be maintained for long periods of time. So if you're doing something for a long term, that's always an aerobic. That's an aerobic process. The anaerobic process can be only sustained for about a minute. So the higher power output cannot last more than about a minute. So this phase, okay. So what is this phase? This anaerobic phase is this ability is useful in emergencies. So for instance, allowing an animal to climb a tree very rapidly, run away, or fight fiercely when in danger. Okay, so this is a sort of a survival mode. To do this, so in this anaerobic phase, the body rapidly oxidizes available blood sugar with oxygen already present in the blood. So you're using all the resources that are already present in the blood. You're not wasting time to go breathe more air and stuff like that. And makes the resultant energy available to vital organs. So your body produces energy with available resources and sends it only to the organs that need it immediately, like the big skeletal muscles and stuff like that, if you have to run away. The heart rate increases to circulate substances more rapidly to areas where they are needed. Blood flow patterns are altered to send more blood to organs active in stress response. So you don't want to send blood to your digestive system at this time. You want to send it to your skeletal muscles. Okay. And then also here's other things that your body does. The spleen contracts to put stored blood into the general circulations, making more sugar available immediately. Yeah. The liver transforms large amounts of stored glycogen into glucose and releases into the circulatory system. Yeah. So glucose can be rapidly oxidized. So all this happens in a minute. All these actions utilize oxygen already in the body, and the higher power output can only last about a minute. Okay. So this stage is called the anaerobic phase because no ingestion of oxygen is needed. Okay. Is You're using the oxygen already present in your body. But again, to get energy from the food, it still has to be oxidized. It's just that you're using the oxygen in your body. Okay. But again, this thing lasts very short time, gives you time to run away and all that. But then if you want to sustain an activity, you have to switch to an aerobic phase. The body quickly becomes oxygen deficient during the anaerobic phase and requires oxygen from the lungs to maintain its activity. So now you enter the aerobic phase, and so if you're going for a long run, these are some of the things that your body does. So to make possible the long-term production of energy, what you have to do is, so since if you're involved in a long-term activity, you're producing a lot of heat, so your body initiates sweat production so you can maintain your core temperature, your body temperature. To dissipate thermal energy, your body you start breathing rapidly, and the dilation of air passages allows you to bring in more air. Okay, so your body does various things to sustain aerobic activity. Okay, yeah. So your body is a complex system. Okay, but the use of energy is fairly simple. So you intake food energy, you 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 do bodily functions and work. Okay, so you spend some of that energy on that. A lot of that, whatever you do, a lot of that is most of it is goes as thermal energy, and Any excess energy is stored as fat. Okay. So chemical energy in food is converted either to work or thermal energy or stored in fatty tissues. Okay, so this is just a conservation of energy principle. Yeah. So energy consumed by humans is converted to work, thermal energy, or stored fat. By far, the largest fraction goes to thermal energy. Okay, that's because our bodies are very inefficient. So, although the fraction varies depending on physical activity. So, for instance, you saw that when you're swimming, only 22% goes to work and 98% goes into thermal energy. Okay. All right, that finishes this chapter. We'll stop now.